I'll, I'll remark that on the style of this presentation, my approach to summarizing the meeting is going to more or less take the overlap integral between what was actually said over the last 4 or 5 days and my peculiar, rather idiosyncratic set of resonances. So I'll comment on a few things that struck me particularly vividly, seemed especially significant, and were new to me about this the grab bag topic of post-merger winds in Kilonovae. It's quite likely that the last category, new to me, means that a number of these comments are really old news to experts in the audience. And I apologize to them for restating what they think has long been obvious. So to begin, my sort of overall impression of what was said about post-merger winds in Kilonovae was in some ways that this was a topic that already seemed to be very complicated. And all sorts of new complications, interesting new complications in many cases, were explored, articulated, and we were warned about. So in that respect, this may be a little bit of a pessimistic summary, but it's also one about sort of interesting things to explore. On the other hand, there was one item I learned just this morning. I had added a slide during the talks that's in a more optimistic vein. So it's not going to be entirely, this is worse than you ever thought. So to begin, I was very struck by the slide that Jonas presented in his talk from the Mumpower et al. Review on the surprising lack of nuclear physics data on basic questions like the mass of various isotopes and the impact that it has on the computed nucleosynthetic yields. These are plots as a function of atomic mass, showing how the yield on a logarithmic scale, notice it's from 10⁻⁵ to 10⁻², could vary within the range of the experimental uncertainties for the mass of the kinds of nuclei that are reached in the R process, which by definition, the R process, are relatively distant from the value of stability, and therefore have short lifetimes and are hard to work with experimentally. And these are some pretty frighteningly large possible error bounds. I'm not sure what can be done to improve the situation, whether through, I'm not nearly enough of an expert in nuclear physics to say whether it can be improved by better calculations or new kinds of experiments to measure these masses. It does seem to emphasize a point that's already been made on the grounds of the very, very complicated spectroscopy of Kilonovae, that what we can speak about tends to be groups of related elements and isotopes rather than individual ones. A second set of warnings that maybe are also opportunities was mentioned by, amongst others, different ways, Shane Davis, Dan Siegel, some other people, having to do with special properties of actually calculating the evolution of these post-merger debris disks. The first one, which Shane mentioned, is that when you're in a highly degenerate state, so temperature is small compared to the Fermi temperature, then in the solution from conserved variables to primitives, it's very difficult to get an accurate value for the temperature or internal energy, whichever the quantities you're actually solving for may be. And this is a recurring problem in disk simulations. Sometimes it's because it's highly degenerate. In other contexts, it's because typical disks are relatively cold compared to the virial temperature. And that means the internal energy is always small compared to the total energy. And In relativistic problems, this can be enhanced by the smallness of the internal energy compared to the rest mass density. But it's certainly a recurring and touchy and difficult problem. It may have particular implications here because the neutrino emissivity is so exquisitely sensitive to temperature. And there are few cooling rates, the radiation rates, that scale like T to the sixth or even faster. Another interesting complication, again, as compared to conventional disk simulations, is that although in the typical situation, actually typical, in some places more familiar situation, all the heating is due to dissipation of MHD turbulence. In these disks, there are a number of other heating mechanisms, nuclear reactions, nuclear decays, possibly neutrino absorption or neutrinos injecting pairs. And that's interesting in a couple of ways. One is that it means there are just more processes going on that need to be dealt with in a reasonable way. Another is that it matters how you treat these dissipation rates. This is an interesting remark that Dan Siegel made actually in the chat following his talk, that the difference, one of the principal differences between doing alpha viscosity models for the disk and real MHD calculations is that the alpha viscosity places dissipation in proportion to the local pressure. MHD somewhat disproportionately puts dissipation in regions of relatively low gas pressure, that is, to higher altitudes away from the midplane, because magnetic fields basically are buoyant compared to ordinary matter. So that means the heat can go into the wrong place with rough guesses about the dissipation mechanisms. And that can have dynamical consequences in terms of, for example, energizing the disk winds. But these multiple mechanisms also raise another interesting point of principle. We're all sort of psychologically trained by Shakura and Sinyaev to imagine that somehow the internal stress is determined by the pressure. That's, the famous ansatz from, close to 50 years ago now, that the internal stress should be proportional to the local pressure. We learned, it's now 5 or 10 years ago, that it's not, if anything, it may be the other way around. If you look at fluctuations in the stress and compare them in terms of timing to fluctuations in the heat content, turns out that the fluctuations in the stress precede those in the pressure. And it's actually for a very good reason. Ultimately, it's orbital shear stretching magnetic field lines that puts energy into the field, gets stirred up, the turbulence ultimately dissipates. That's where the heat comes from. And only then can the heat go into the internal energy and the pressure of the gas. So it's from MHD dissipation to pressure rather than the other way around. So now we're in a situation in which dissipation of MHD turbulence isn't the only game in town in terms of heating rates. And it raises this question of principle of whether the relation between pressure and stress in the long-term time average, which comes out of a great many global and stratified shrink box MHD simulations, may not hold up exactly when there are other ways that the gas can derive its heat other than MHD dissipation. And in fact, it's possible that in the MHD neutron star merger debris disk simulations already done, that there is data out there that hasn't been looked at in terms of this question that might speak to this. I'd be interested to talk to people who've done many of these already. And of course, we will soon be doing some of these as part of the TCAN collaboration. The next complication has to do with nucleosynthesis itself and basic parameters governing it, for example, the electron fraction YE. To give an illustration of how the assumptions can matter, I copied this figure from a recent preprint by Just et al., in which they tried different prescriptions for heating. The orange curves there are MHD, but the text of the paper is so cagey about resolution and so apologetic about it, I have to assume that it was under-resolved. The blue curves are a peculiar approximation to this viscous model having to do with viscous length scales. The black curves are an alpha model. Thick and thin has to do with including neutrino absorption or not. Thin lines don't, thick lines do. So what you can see from that figure is that in the outer region where you might think you're expelling the Kilonovae wind, how that the stress is treated even in this way can make a pretty significant difference, because for YE, factors of 2 are important. So now let's sort of step back and think about how the system all the complications within the system. One is that the YE at the wind base could be largely dominated just by local nuclear processes. On the other hand, there are definitely regimes in which the neutrinos radiated from the inner disk come out, enter this wind base, and are numerous enough that they could alter YE. That's basically some of what's going on in the contrast between these curves. Another one is, following back on that, is that if this is true, then the neutrino intensity at the wind base, where the nucleosynthesis is happening, depends on the heating in the inner disk, because that's where the energy for the neutrinos comes from. This in turn, excuse me, depends on all those complications I just mentioned about what goes into the heating, and that possibility that the heating and the MHD stress interact with one another, which in turn changes the disk's surface density profile, because the stresses are what cause the mass to move in or out. And that's also interesting because the time scales for reaching inflow equilibrium in the disk, particularly out beyond 100 M or so, are not small compared to the duration of the event. So it will matter what the initial state is for the debris disk, basically how the matter is placed into orbit by the events of the merger. And all these different processes that control how matter gains or loses angular momentum will affect one another as the matter moves in, mostly in the inside, and outward, mostly toward the outside. These non-equilibrium flows could also perhaps have interesting effects on the division of the disk into the regions laid out, I think this was in Ari's talk, about where neutrinos are trapped, where they diffuse out, where it's optically thin, etc. Okay. Still, another interesting monkey wrench that got tossed in is the degree to neutrino transport. Here, different aspects emphasized by Jonah Miller particularly, and another one by Dan Siegel, both conventional transport in terms of absorption and scattering and so on, but also unconventional in terms of flavor conversion. But all of these can affect the neutrino intensity out in the nucleus synthetic region. There is also a possible consequence of flavor conversion that I learned about from Luke Roberts a while back. If absorption is important, flavor conversion amounts to a kind of get out of jail free card. Because for all the time that a neutrino spends, let's say, as a muon type, it can travel freely within the disk. Nu mu has no opacity on ordinary matter, electrons, protons, neutrons. So the conversion to nu mu allows electron or anti-electron neutrinos to travel freely for a spell, get closer perhaps to the surface, and if only out there they flip back to electron type, the emission rate for neutrinos could actually be increased by mixing rather than decreased. So there are a lot of nonlinear connections here. But now, for a slightly more positive note, I was very struck by what David said a couple of hours ago about the connection between the mass of the debris disk and the properties of the merger itself, either the mass ratio or the equation state in the neutron stars and the strength of that bounce shock. And that could be a very powerful connection. A question I'd like to ask, because maybe should have emphasized this at the beginning already, is that I'm still very much learning my way through this subject, is just how linear or at least well calibrated the relationship is between mass in the disk, mass in the outflow, and the luminosity of the outflow. It seems to me a very good bet that if one increases, the others do also, but quantitatively how they do it and how that scales is a little less clear. Nonetheless, it's still very encouraging that there does seem to be such a strong connection between this basic property of the disk mass and the mass ratio of the event, or perhaps the actual equation of state. So having warned you about all these things, I'll just say that there is some good news in the end, because in fact, doing self-consistent physics of exactly the sort that will be necessary to sort out these issues is exactly what we're hoping to do. So we should have lots of interesting work ahead of us, and we're not going to run out anytime soon. Stop there.
Okay, thank you very much, Julian, for this very interesting overview with your own perspective. And let's clap our speaker and start the beginning of the last discussion of the workshop. Okay, we are up for questions. So, okay, so if no, okay, I'm waiting for questions. If not, I'm going to ask you. So concerning the good news that David this morning told us, and I'm still very interested about this eject bounce that he talked about, and how that, I mean, in his simulations, if I'm not wrong, you didn't have MHD. But I'm curious to know whether there is, you think that there will be some effects to MHD to that, to those relationships that you are talking about, especially in the ejecta, in the bounce stage.
Oh, I'd be surprised if magnetic fields had anything more than a very minor effect. I mean, they're energetically really trivial in the star, and they're at those near neutron star densities when the bounce is taking place.
This is taking place after the merger, right? So after the Calvin-Almond
It's in
instability.
the course of the merger. It's right as the densities at the center reach their maximum. That's what the bounce is all about. So once this stuff is pushed out, it has its energy, it's headed outward, and any further sort of hydrodynamic interactions are going to be probably dominated by the fluid mechanics. Because they push, as this fast moving stuff pushes through the slower moving stuff that's out a little farther. So it doesn't seem like a place where MHD would make a whole lot of difference. That comes in later in the story. At least that's what I would expect.
Okay, so there's further room for more questions.
Well, maybe exhaustion, saturation, and hunger have taken over.
I
Maybe.
have a comment if I can. Yeah, it's back on that nuclear variation plot that you showed right at the beginning, and you had asked what is there to be done about nuclear variation or these nuclear uncertainties, and to be honest, it doesn't look great. There are experimental plans to get further out in neutron richness, but even for the art process, that's not close enough. It's still going to help, of course. Any new measurements are going to help. But that's on the experimental side where that is. There are plans, notably through FRIB, the Facility for Rare Isotopic Themes. But then there's also this question of fission too, because if we expect these art process elements to come from these conditions that can give rise to fission, and that just brings up a bunch of other uncertainties too that are beyond just the question of the nuclear masses.
Actually, could I ask you a question?
Please.
You mentioned fission. I was thinking about this a little bit, trying to dream up an experiment that might actually help. And I was wondering whether the neutron fluxes coming out of reactors would be a useful thing, and just stick some of these isotopes into that beam of neutrons and make those neutron-enriched isotopes, at least in some very small numbers. Would that be a feasible experiment?
Yeah, I think that is being done in some places. But the problem is the fission that's actually relevant is stuff like plutonium-320, which is just,
just using the neutron flux from the ordinary reactions in the reactor, spew out a whole bunch of neutrons, and then put samples of these of nuclei such that if you add a couple of neutrons, they're in the R process range, or at least on the R process pathway, bleed them off, measure their masses.
Yeah, as far as I know, that's essentially how they do it.
Okay.
It's way more complicated than that, but yes, that is
I'm
being
sure,
done.
I'm sure.
Yeah. Plus, I'm not an experimentalist, so I don't know, but I know that they're using as much as they can, and I think that is one method they use. And then on the kind of the theoretical side too, another thing that is being done is just to be consistent wherever possible. So when these theoretical rate calculations are being done, sometimes things don't necessarily match up. You'll use one model to calculate the decay rates and one model to calculate the reaction rates. And it's not that they're being lazy, it's just a hard thing to do. So one thing that is currently being done is making sure that all the rates that are calculated are at least consistent with the same nuclear mass model. So whether or not that's accurate is another question, but at least it's all consistent in itself, if that makes sense. But yeah, it's hard. Unfortunately, there are so many uncertainties there. And if we want to use things like Kilonovae or even stars and other things that rely on the nucleosynthesis, then that's a huge barrier that we have to overcome.
Okay, I see Svi has a question.
Svi?
Well, as you see, I'm back to the meeting, to the last moments of the meeting. Actually, I have two remarks on the last comments. One is that, as far as I know, these experiments were not done so far. But as far as I know, a good friend of mine, Michael Paul, is doing the first star process experiment with a laser with a laser facility, in which the idea is to produce using a laser facility system which produce a lot of free neutrons, and to have our process, but this will be only with light elements at this stage. And the reason that I know that these experiments were not done so far in other ways, because I read the proposal and it is stated there several times that this is going to be the first ever man-made R process experiment. But going back to your other question, to other remarks, you talk about uncertainties. There are huge uncertainties in the nuclear data, but there are even larger uncertainties in the atomic data. So I don't know if you mentioned those, but the system is really complicated, because we are fighting here with a situation in which there is not enough input on the basic physics, which in principle could be obtained somehow, but it's not available.
Okay, and when you say atomic data, are you speaking of ionization recombination rates, or line opacities, or
both.
Everything.
For these materials, first of all, there is a huge number of lines. There are only approximate methods to calculate them. And as far as I know, there are extremely few experiments on this element. So there is little to calibrate the theoretical calculation against with. So this data is simply not available. And the most critical one is the opacity.
And anytime you get more than 10 or 20 electrons in an atom, it gets really tough.
Okay, let's see if there are any more questions or comments. Last comment or question before we all, I think, take our due rest from the workshop. So if not, I think I would like to really thank everyone who has been sticking around for so long. This has been a very long week, but as well as a very interesting week. From my perspective, we learned a lot. And I want to thank all the speakers and all the participants and the chairs and the leaders of the discussions for having made this really a very exciting workshop. I think we all agree we had some fun, although exhausted. We have been kept on everyone busy in the discussion session way beyond the almost 2 hours that was allocated for that time. So that's, I guess, a good sign. And there were also many questions during the talks. Many questions went through the chat and the Zoom. I would actually, re-emphasize, and thank you, Jeremy, for helping me on this, to actually use the Slack channel that we have created for this workshop to continue to have these wonderful discussions. I think we have many more questions, certainly, and I would like to make sure that we continue to have this conversation online, at least until we can meet in person again. So I want to thank everybody, and I want to thank also the organizers. So the organizers of this workshop, so the Scientific Organizing Committee of Federico Lopez Armengol, who is a postdoc here at RIT, who's been working on the Tican handoff, Ariana Murgia-Bertier from UC Santa Cruz, Julian, of course, who I just spoke, and then the local organizing committee made by Tim Moon, who is our essentially program coordinator. He's he's been behind all the aspects of the workshop, keeping us on track with all the recording, all the talks that you see on our website, and other things. And then Chin Yi, who is our administrative self-support, who has been monitoring us and making sure that if we weren't muted, she muted us, and making sure that everything was in order during the workshop itself. Jim Healy and Josef Lochover for having made the technology aspects associated with this Zoom workshop go very smoothly. And so thank you everybody, really. Again, I hope that we learn a lot, and I hope that by having all we have been discussing online will allow other people who haven't been able to attend all the talks to learn a lot and enjoy and follow up on discussion. And if you didn't have access to the Slack, or don't know about the Slack channel, and you just joined this workshop maybe in the middle or at the end, because I see some new names on the participant list, which I think went over hundreds in total of people that participated. So if you want to access our workshop Slack channel, please contact us. I think this is totally open. Obviously, we don't make it public because we want only people in the field to sign up. But please be aware that everything is open and that you can access all the information. So again, thank you very much, and have a good weekend and a nice break. And thank you.